Okay, so yesterday what we did was, last lecture that is, we worked out the Hamiltonian density rather for and for positive definiteness of H, or it is easy to see that the first two terms are positive definite. So, it really is a condition on the potential. So, we need to write u of phi should be greater than 0 or equal to 0. I think yesterday in the last lecture I put a modulus here by mistake, that is not correct, and so we saw some examples of this. So, suppose you are given a potential which has which is bounded from below with some other number, you can always add a constant and shift it so that this satisfies this condition. Okay. At least in the in quantum field theory, also there is nothing which fixes the 0 of the energy. You need to couple to gravity to see that there is a 0 point energy, etc. Okay. So, so this is a condition we will assume. Any potential which is bounded from below will satisfy this, and so let us consider a sort of a nice example of something like this. Suppose so this is phi u of phi. So, we have this, I am just choosing a very specific example where there are two values for which it achieves a minimum which is 0. Okay. So, let us look at the lowest energy configuration for this. So, sometimes this is called the vacuum configuration. This terminology borrowed from quantum field theory, but we will just call it the vacuum. So, we can get these two terms to be 0 by choosing. So, let phi be time independent as well as a constant in space. So, basically what I am doing here is that these two things go to 0. So, the Hamiltonian for such a configuration. So, let us write that as phi equal to some constant, and so for such things the Hamiltonian density would be u of the value of constant. Okay. So, clearly the lowest energy configurations happen where when u of phi takes its lowest value. Okay. So, this is equal to 0 when, in this example, more generally for all the, when phi 1 is equal to phi 1 everywhere, or phi is equal to phi 2 everywhere. Okay. So, this is the lowest energy configuration, but now the question is this a classical solution? Okay. By this I mean, is it a solution of the equations of motion? And so, we had worked out the general equation of motion, but we have not worked out the equation of motion for the Lagrangian density, which, so let us do that to complete the story. So, okay. So, we need to evaluate this object. So, this will just be d mu of phi and of the field phi. The derivative of this, it comes only through the potential, and so this is equal to minus u prime of phi. Okay. So, the Euler Lagrange equation which we derived earlier tells you that equal to dl by d phi. Okay. So, we get d mu acting on dl of phi, which is this. So, this implies okay. So, we can take a few cases before we come back to that thing. No potential. Okay. So, this term is 0. So, this you get box phi or the D'Alembert phi equal to 0, and this equation is the massless Klein-Gordon equation. Second case is to take u of phi equal to m square by 2 phi square. Okay. This satisfies this thing which I wrote. It's just if you plot u of phi versus phi square versus phi, you just have a parabola. Okay. So, if you rewrite this again, we can work out what u prime of phi is. It is just m square phi. And so, what we get here, so now this equation gets a contribution out here, there is a minus sign out here. So, I can bring it to the right hand side and I get box plus m square phi equal to 0. So, this is the massive okay, there where m is the mass, rather the mass square. Okay. Yeah, I should I actually in all these things I have set we will get back to this. I have set c equal to 1. We will discuss this a little later. This is part of something called natural units. These are units which are natural to the problem, like we saw like we went from SI units to Gaussian units when we considered Maxwell's equations. Okay. So, that was natural to special theory of relativity, and setting c equal to 1 sort of gets rid of this. So, remember we said x 0 equal to c t and x I were the. So, if you put c in coordinates where c is equal to 1, then there is no distinction between t c and t, x 0 and t rather. Okay. So, this is so you may have seen, if you look at books, there might be powers of c going with this thing. That is one thing. There might be, you might find that some other books also have a minus sign out here. This again has to do with the sign convention that people follow. Okay. So, but at the end of the day, this equation is the same equation depending on your notation. So, whenever you take any book on classical field theory or even quantum mechanics discussing relativistic quantum mechanics, you need to check the signature of the metric. So, in other words, you eta mu nu in this course will be always +1, -1, -1, -1, but there are books which follow the reverse convention. Okay. So, we follow this convention. So, these two equations are nice, they are linear. Okay. So, you can see that if I have a potential which is quadratic, then I am guaranteed to have a linear equation. Okay. But we could try more general things. So, suppose I could add, let us say we took u of phi to be m square upon 2 phi square plus some lambda by 4 phi power 4, okay, some quartic interaction. Then you see that u prime of phi becomes m square phi, but now you get a lambda phi cubed. Okay. So, the equation is whatever is this equation is no longer linear. In other words, if you give me two solutions, superposition will not work. Okay. So, now coming back to coming back to this equation, this is the most general equation, and we asked the question, if we choose phi to be time independent and a constant in space, is this a classical solution? Okay, so let us come back here and ask the following question. You see, a box just consists of space and time derivatives. So if phi is a constant, this term vanishes. So it will be a solution of the equation of motion, where when u prime is equal to any of the extremal points out there. Okay, so what we see is the answer is yes, since u prime of phi is equal to 0 at phi equal to phi 1 or phi 2. Okay, suppose we, let us say that, let me be perverse here and choose some more, call this phi 3, call this phi 4. So clearly I can have classical solutions, for instance like this one phi 3, where u prime of phi equal to 0. So there is definitely a solution which says phi equal to phi 3 for a constant which is phi 3, because it satisfies the equation of motion. But remember, the action principle just tells you that it is an extrema. So then you come back here and look at this, and what does this tell you? That the energy of such a configuration is infinite. Which one? Yeah, this one is infinite, because it is a constant, but the value of this function is some finite number. Okay, so the energy density is constant, but that implies that the total energy, which is the integral over space time, blows up as the volume of space. Okay, and similar thing rules out even this solution. Okay, so it is important to note that these are indeed solutions of the equation of motion. Is that clear? Okay. So yes.
Supposing you shifted a bit lower, so you get the other state at 0 and two states at some negative value.
Yes.
So then you might as well say some states can't have a negative infinity of energy.
Yeah. So that is the point I said earlier. Yeah. Suppose there is no scale, nothing which sets the scale of energy, so I can shift things up and down. So I could do something like what you are suggesting, is to take let us say we choose this as your energy scale. Okay. But now then the lowest energy configuration nevertheless still remains phi 1 and phi 2, but that will be some negative infinity. So but you know that you want to measure things with respect to the ground state or the lowest energy, so you shift things and go away. So that you can always do. Okay, because nothing changes. See, adding a constant to this does not change the equations of motion at all, but it does change what you mean by 0 of energy for sure. Okay, and so I am using up that freedom to take care of this ambiguity. Okay, so it is true that this exists. So I understand what you are saying. I mean, the point here is that you have some idea of stability or whatever in this neighborhood, and you can, if you jiggle things, there is a nearby solution which is probably lower energy or whatever. That is what one has in mind, but in that sense this would be okay. This is like a local minimum, but it is worse, because what this is, the thing is that this is a Hamiltonian density, not Hamiltonian or energy density. Okay, so but the fact that you have more than two classical, so here is a case where we have degeneracy, in the sense that there are two different ground state solutions, and so by here degenerate I mean equal energy solutions, two degenerate in vacua, which is phi equal to phi 1 and phi equal to phi 3, sorry phi 2. So now let's stick to spatial dimension being 1. So we are in 1 plus 1 dimension. So another notation, when I will write 1 plus 1 plus d dimension for pointing out that there is one time like in d space like. Okay, so usually this is what people do. This also is to remind you that there is a signature in the metric that this is plus and this is all minus. So, it is reminiscent of that, but if you are talking of Euclidean space, I would just say d plus 1 dimension, then there is no signature. Okay. So, we will choose d to be 1. So, we are in 1 plus 1 dimension. So, space is just one coordinate, and so now I can ask again, I will stick to, I will still choose, I look for solutions which are time independent, just to simplify things. Okay. So, we look for and I will put in another condition, and you will see that it is a strong condition, and finite energy. Okay. So, finite, remember finite energy is not the same as saying that your Hamiltonian is finite. We already saw examples, the Hamiltonian density is finite, it does not mean anything. Okay. So, what we want, so what we really want is, actually I should not be calling this the Hamiltonian density, I should just call it the energy density, because the Hamiltonian is a function of the conjugate momenta, while this I have written in terms of phi dot. Okay. It is only semantics, I could in this case pi is just phi dot, I could write pi square, but the arguments are important. So, the correct statement is just energy density. Okay. So, yeah, so what we want is integral of dx from minus infinity to plus infinity of h must be. So, this is the finite energy condition. Okay. So, yesterday we discussed fall off behavior, and that tells you that the key point was that it should go to the, yeah. So, let us mark, so we want to plot phi versus this thing. So, let us say this is phi 1, here what phi 1 was negative and phi 2 is positive. So, let us respect that, let us say this is phi 2. Okay. So, coming back to this term is 0, but there is a gradient term and there is also u of phi. So, let us first focus on u of phi. If u of phi has to give has to give a finite contribution to the energy, then this should go to 0. So, but now we can see, let us look at x equal to plus infinity, we see that there are two possibilities, u of the phi should go either go asymptotically to phi 1 or phi 2, there are two possibilities. Similarly, out here there are again two possibilities at minus infinity, okay, which is again phi 1 and phi 1. So, let us consider the case where both sides plus and minus infinity is phi 1, then the lowest energy configuration is nothing but the one which we already looked at, that is the vacua. Again if we take phi 2 at both ends, that is again the same solution, but now there is a possibility of a solution which interpolates, a solution which starts from say phi 1 on the at minus infinity and goes this way. It has to have some shape of course, and we do not know the shape, but okay. So, clearly this condition requires limit x tends to infinity, phi should go to phi 1 or phi 2, and limit x tends to minus infinity, phi should go to, I am just writing out what I just already said in words. So, we will have something like this, but now clearly gradient will not be 0, unlike the vacuum case we need to, because it has to change somewhere, but the rate of change has to be such that. So, again this should have certain fall off behavior, but the key point is, even though we may not be able to solve the equations, see it is obviously this is some horrible nonlinear equation, and in principle we cannot solve for the Euler Lagrange equations, the box which I just erased out here, we cannot solve for the Euler Lagrange equation, but I claim that there has to be a solution with this asymptotics. So, this is a claim, there exists a solution to the equation of motion such that phi tends to phi 1 as x goes to minus infinity, and okay. So, an interpolating solution, and the reason is as follows. So, there is one way of understanding this. So, this is like this is like the analog of writing the trajectory of your problem. It is not, it is a trajectory in space, but it does not matter, we are extremizing the action. So, I can keep varying this thing, and somewhere I have to hit the I have to when I am talking about this number. No, Allahabad and all is different league. 50 degrees centigrade outside. Okay, yeah, okay. So, the claim is that there exists a solution to the Euler Lagrange equation of motion such that phi tends to phi 1 as x tends to minus infinity, and phi tends to phi 2 as x tends to plus infinity. One thing you can say is that by just flipping the axis, I can if I can find a solution with this asymptotics, I can definitely find a solution with asymptotic phi goes to phi 2 as x goes to minus infinity and the other one. Okay. But there is a very nice way to see this. The first point is to since you have fixed the boundary conditions at these two ends, you really cannot tamper with these guys, but what you could do is to keep changing this thing, jiggling it such that the action is being extremized. So, there should be something, okay. But there is a much more important reason for this, and this has to do with the fact that this solution carries some charge, conserved charge, which is different for this as compared to the vacuum solutions which we looked at. So, let us see how that goes. So, since we are in 1 plus 1 dimensions, the Levi-Civita tensor is epsilon mu nu. I just define it to be, this is equal to plus 1 for mu equal to 0, mu equal to 1, minus 1 for mu equal to 1, mu equal to 0, 0 for the other one. Okay. So, I will define a 2 current which is okay. So, last lecture we saw that if I give you a current which is conserved, then from that we get some charge by integrating. Okay. So, first I have to show that this is conserved. So, let us look at d mu j mu. So, in this mu and nu only run over 0 and 1 because we are in 1 plus 1 dimension. D mu j mu equal to 0. So, let us see how that goes. Okay. So, now this is antisymmetric while this is symmetric. So, this has to vanish. So, the amazing thing here is that I did not use any equation of motion or anything. So, this is conserved. The Noether currents which I mentioned last lecture will be conserved modulo equations of motions. That is something we will see. We have not derived it, but this is easy to see because this is antisymmetric and this thing is antisymmetric, and while this is symmetric. So, if you contract something symmetric with antisymmetric with something symmetric, it has to vanish. So, now the neat stuff is, let us ask what is the charge. So, charge will tell you it should be q of j 0 integrated over space, but what is j 0? It is epsilon 0, then this can be only 1 d 1 which is dx of phi. But this, what is this? It is just the value of phi at plus infinity and minus infinity. But those are your boundary conditions. So, you can see that the vacuum solutions correspond to having charge 0, while this particular solution has q equal to phi 2 minus phi 1, while the like I said, remember I told you the flip solution will have charge phi 1 minus phi 2. So, the key point is that there is is that since this is a conserved charge, but it translates here into the statement that the asymptotics are never changed. So, whatever you do jiggling out here, you should find a solution. So, all I am saying, it is actually not a great statement, that there exists a solution in this class, in this with q equal to phi 2 minus phi 1 with finite energy. So, even though we do not know the explicit answer, because it might be a horrible differential equation, a difficult differential equation to solve, we know that such a solution can exist. But there are special potentials for which there exists a solution. Okay. I mean, you can write out an analytic expression, and that is something which will come for you in one of your assignments, probably the next one, where you will actually go back and check. So, these currents like this, which are conserved without using the equations of motion, are called topological currents. Okay. So, they are not associated with any symmetry or anything else. So, actually the precise statement is that the symmetry should be continuous, otherwise you do not expect symmetries. So, where you have some parameter that you can vary. Okay. So, I will just make the statement of Noether's theorem, and we will discuss this. Okay. Given any continuous symmetry of a Lagrangian of an action, say, there exists a conserved current. Okay. Modulo equations of motion, this one. Okay. So, in other words, so if you write out the current and you want to check that it is equal to 0, if you get the equations of motion, you set that is equal to 0. So what I mean by that is some equations of motion are something like this: dl by d phi modulo this. Okay. So, this is something which we will prove in increasing generality in this course, but right now we will just use this to prove that there exists a current for translation in space and time, which we will call energy and momenta, would be the conserved charges. Okay. So let us see how. So before that, let us understand what we mean by this. So first, let us understand what we mean by a continuous symmetry. So we already seen in groups that there are discrete groups which have finite number of elements. There are also continuous groups like the rotation groups. Okay. So the key point is, if you have a group like say Zn, there is no notion of smallness. You just have a bunch of elements or a neighborhood of an element. But if you have a rotation, by some angle theta, there is indeed a notion of small theta. Okay. So you would write r of theta is equal to identity. So when you, in other words, if I set this parameter to 0, it is close to identity, and so I get plus some order theta term, and it is actually an infinite series. So there is this notion of smallness of some parameter, etc., and you will have a bunch of parameters. So if you have SO3, you will have 3 parameters. Okay. So I can actually, if I start from the identity matrix, I can go in 3 different directions, roughly speaking. I can turn on any one of these parameters. Okay, the Euler angles, I get 3 parameters. What this tells you is that for every such parameter, there is a conserved current. So if you have a rotation of SO3 kind of invariance, it tells you that you will have 3 conserved currents and conserved charges. Okay. If you have n parameters in your which parameterizes your continuous symmetries, then you will have n independent currents. So the example which we will look at now is that of translations in space and time. Okay. Let us put a tilde here. Okay. So what do we mean by this? That so a mu, now we are not no longer in one dimension, that was just for our example, we are coming back to d dimensions. So we see that there are d plus 1 parameters. Okay. That is a0 up to ad. Okay. So what we would expect, so one expects d plus 1 currents Okay. So, now the current should carry an extra label which is the parameter label. Okay. So, what we will do is, so we will write something like this, d mu j mu nu equal to 0. So, here this nu is actually refers to these d plus 1 parameters. It is a little bit confusing in the following sense that this index, both of them run over the same thing. Okay. So, what you get is conventionally called T mu nu, not J mu nu. Conventionally, these currents are called T mu nu, okay, and it is called the energy momentum. And as things stand, mu and nu are actually distinct indices, they have no relation. So, all this says is that d mu of T mu nu equal to 0. This is the statement of, if you just take Noether's theorem and it tells you this thing. It does not tell you anything about the nu index. It will turn out that we will find in at least the first example which we look at, but not generally true, that this will be symmetric under these two things, but as it stands there is no property. Okay. So, I have to actually it is now notation, I have to tell you which is my current index and which is my parameter index. So, I have just chosen a convention which says that the first index is the current index and the other one is this thing. So, now we can ask, so what are the charges? So, you will find the charges, I will just call them P mu, I can just define it to be the 0th current part of the current. This is what you would call it. Okay. Oh, let me use the same index which I used there. Okay. And if you integrate over d dx of P nu, you will get the conserved charges which I will just call P nu. Okay, there is a lot of notation, but it is important because it is confusing at first that the same index structure arise from these two. Okay. So, now we need to now at least work out this theorem for this particular symmetry, which is what we will do now next. So, obviously you know that from classical mechanics in normal systems, you know that if you have translation invariance, momentum is conserved, linear momentum and this thing. So, but in a complicated system, this the conserved charges which are associated with translation symmetry are called energy and momentum of the system. So, this is the definition. So, what I wrote as H is nothing but T 0 0, okay, because it is associated, it is the thing associated with the parameter for time translation. Spatial translations would just be the other guys. Okay. So, this is okay, that is why this is called the energy momentum tensor, sometimes called the stress tensor also. This is from continuum mechanics, this thing. Okay. So, let us now try to prove this. So, the question is, when does one have translation invariance? Okay. So, we have already seen the argument that there should be no explicit dependence. Okay. So, the action on space time coordinates. Right, then we expect so in other words, so the ones which we have been looking at so far, the actions, we never had any dependence on coordinates, we only had dependence on the fields and their derivatives. Okay. So, so now let us go back to these symmetries and ask what happens. So, let us say that x tilde mu is x mu plus a mu. Okay. So, what does that imply for the field phi? So, if you make such a coordinate transformation, it is a scalar field. So, you just define phi tilde of x tilde should be nothing but the field phi of x. So, let us just take a simple example to understand what we mean by this. So, this tilde is just this coordinate change, but this tilde here indicates that the function has changed. So, suppose you have just a simple function f of x in one dimension and you change its argument, let us say it is x square, and you change its argument, then you get a new function. So, saying that this is equal to f of x, what does that mean for this function f tilde? So, where x equals x tilde. Okay, so, you go back and plug this in here, says that f tilde is equal to x plus f tilde of x plus a equal to f of x, or equivalently f tilde of x is equal to. So, now we can go back here and okay. So, mathematically speaking, x square and the function x minus a whole square are not the same function, right. So, that is what we are indicating here, and this is just that simple statement that this is what this lets you derive what this is. And so, now I had defined yesterday something called delta bar, which was the change in the functional form. Okay. So, what is delta bar of f of x of f of x? That should be how that should be defined to be f tilde of x Okay. So, let us plug this, let us look at this. So, according to this, this is just f of x minus a and let us expand this thing to first order in A. Neglecting terms of order A square. Okay. So, as I pointed out yesterday, delta bar has the advantage of delta bar commutes with taking derivatives, in this case taking the derivative d by dx. So, in fact, the confusing part is that normally you would just blindly say, oh, let me take delta of f of x to be f tilde of x tilde minus f of x. That is what you would have first written, but that is 0 in this example, because you are changing the argument and the function. So, you are doing this double stuff. So, but that delta will never. So, you could define I mean, let us forget that it is 0 for this for a moment, but the point here is this object, this will not commute with derivative, because if you are doing a shift in x, I mean it actually has two arguments implicitly. So, it messes, I mean, so this delta with derivatives. Okay. So, in fact, you may say why should we even look at such a thing like this, but you will see that it is natural in some instances, you will quickly write something like this, but you should remember that whatever is this delta, it will not commute with this thing. Okay. But we can actually, in this example, we can even go back and say how is to, at least we know things to first order in A. Let us ask, can we ask what delta should be. So, let us work that out. So, delta of f of x is equal to 0, but I will show, we can see that this can be written also as that is a minus sign, right. Okay. So, this is what you get, tells you, and it shows you that there is some derivatives acting. So, it matters, ordering matters for this guy. Okay. So, now coming back to this thing, this example, it is the same story out there. We can work out what delta bar of phi would be, but that should be just by definition phi tilde okay. This is just definition, the functional form, how it has changed, and this is following a similar argument. It is just there are many more derivatives. So, this would be minus but even the Lagrangian density is a scalar. So, I can actually think of what happens to the same thing out here. So, for Lagrangian density also I can define delta bar of L, and following similar arguments you will see that delta bar of L is nothing but minus a mu in a mu of phi. Of L, sorry. Okay. So, the statement that it is a symmetry can be written, if you wish, as saying that delta L is equal to 0, and we will use that kind of formula, but this is equal to okay. So this just tells you that the action the yeah, this is it. Okay. So let us see what this we can expand this out and see what this means. So this has a bunch of terms. Into delta bar of plus okay. So it has two arguments. So the reason for working with delta bars is here that it commutes with d mu. If I had tried to work with delta, it will be a big mess. So that is the key, the fact that delta bars commute with this thing is very important. So now I can just go ahead and exchange these two guys, and so we can just use plus. So I can exchange these two. So I will jump one step and write this as d mu of delta bar of phi, and so this will be equal to, and I can integrate by parts, plus the other piece which I have left out, which is okay. This is the total derivative which I have. The reason is that this is a equation of motion. Okay. So I should say 0 equal to all this. So what I get, so now I still have to put in delta bar of phi, which is minus a mu d mu phi. So I get and delta bar phi is modulo equation of motion. Okay. So we started here, this is just a statement of it being a symmetry, and then I convert it to this statement, and I am always working to order a square, I do not need the a to be very large. Okay. So this is what I get. So now we look at this, if you so I have to take care, see I have used up the index mu out here, this is a nu. So I can just pull out a nu and ask what remains. Okay. But now I have a problem in the sense that this has an index mu. Okay. So yes, there is a minus sign. Okay. So let us see, let me redefine this to be nu, and let us call this mu, just dummy indices so I can pull things out. So this becomes a mu times actually I want to do the opposite to match what I had earlier. Let it remain as this is. Okay. So and let us pull out a nu. Okay. Okay, so this is what I have to do. So, this has to hold for any a. Okay, so, that will just imply that this object is definitely true. So, we just define whatever we get here, and then there is a slight problem in the sense that I have a nu in the denominator. So, I can multiply this whole thing by say eta nu rho and convert basically I want to raise all indices out here. So, I get d mu of eta nu eta mu rho L minus d L okay. So, this object I will call T mu rho with a minus sign. Convention has to do with this. So, I choose put a minus sign out here. So, we get a nice formula. Okay. Now, in this here what has happened is that the rho is the parameter variable for the parameter and mu is the current part. Okay. So, that is what we have here. So, this is equal to, because I am taking care of the minus sign now. Okay. And let us evaluate this for the action that we have. It is just okay. So, this is what we get, but now you can see here what we have here is very nice. There is complete symmetry between mu rho. This is trivially true, eta mu rho is the same as eta rho mu, but these two are also the same. But I just want to tell you we got lucky, but it turns out that we can always make it so even if we did not get lucky, as we will see in some examples. Okay. And let us just check what T 0 is. Eta 0 is 1 for us. Okay. This is exactly what we wrote yesterday. But while we are at it, we can even ask what are the other guys. So, let us look at T I 0. T I 0 will be just d I phi into phi dot. Okay. I just stop here. So, these would be the charges, conserved charges. So, this is what I would call P I. Okay. So, we will continue next time, we will look at this a little bit more. We will come back to a more detailed derivation of Noether's equation in much more generality. We will derive a master formula, but that is down the road. What I wanted to get for you is show you that there is a method, given a symmetry you can get. So, this is the correct definition for what you will mean by energy and momentum in any field theory. You get the conserved current and then the conserved charges are what are called energy.